Very often, we encounter situations where an object is constrained to move on a surface. One of the most common cases is the case of the inclined plane. Here, gravity is the force acting on an angle with respect to the direction of motion of the object, forcing the object to slide down the surface. To determine the motion of the object in these situations, the angle between the force and the plane is usually given. Unfortunately, for the inclined plane, more often than not, that angle is not given. But what is given is the angle of inclination of the plane itself. Since we want simplicity when we first study a phenomenon, we will consider the case where there is no friction so that our focus is on what happens under the action of one force. Its weight will be the only force responsible for its motion. Of course, there is one more force acting on it, the normal force, coming from the surface in contact. But this force is not responsible for its motion. You will see it in a moment. Obviously, from our experience with the real world, we know that the acceleration of this object must depend on the angle of inclination. No inclination, no motion. Some inclination, and it will move. And once the inclination is 90 degrees, then it becomes a case of free fall. We will start by picking a coordinate system. Since the object only moves in one direction along the surface, it makes sense to use a coordinate system with one of the axes pointing in that direction. This way, we will be concerned with what happens with one coordinate only. To decompose the force of gravity in this coordinate system, we need the angle between one of the axes and the force. We will get that angle from the angle of inclination of the plane. So, look at this triangle. Since these two lines are parallel, the angle here is also theta. It is the same inclination. The other two angles are 90 and alpha. Alpha is unknown. But what we do know is that alpha plus theta is 90 degrees. And if you look at the intersection of your coordinate system, these two axes make 90 degrees. So, if this is 90 and this is alpha, then this must be theta. We know that sometimes students have a hard time visualizing the geometry when their coordinate system is on an angle to them. If that is your case, in order to not get confused with the angles, you should rotate the piece of paper so that the x-axis is horizontal to you. Rotated like this, the problem should look more familiar. As usual, the key here is to break the vector into components that are in line with the coordinates that we picked. The one on the y-axis comes with the cosine of theta, while the one on the x-axis comes with the sine of theta. Notice it is only the x component that contributes to the motion of the block. The y component is related to the normal force coming from the surface. Since the object does not move in the y-axis, the sum of forces in that axis must be zero. These two forces need to cancel each other, and that can only happen if they are equal in magnitude. With this, you can find out what the normal force is. Since the object does move in the x-axis, this force must be the mass times acceleration. And this is how you find the acceleration. You can always check your results by considering those cases that are familiar to you. As we mentioned in the beginning, if the angle of inclination is 0, then the acceleration is 0, and the normal force is just mg. This is exactly what you get if you replace theta equals 0. If the angle of inclination is 90 degrees, then A equals g, and the normal force is 0. And this, again, is exactly what you get by replacing theta equals 90 degrees.